Floating roads layered in the sky, foldable cars parked like suitcases, and jet engines powering the gigantic metropolises. For almost a century, movies, Jetsons-style cartoons, and science fiction series have convinced us that this would inevitably be the picture of our future. But the physics and economic feasibility of the real world have proven that science fiction got it really wrong, at least when it comes to design, okay? Flying cars weren't born with roaring turbines and flames coming out of the exhaust. They actually appeared powered by electricity and guided by artificial intelligence. Today, in this episode of Amazing Reality, we're going to analyze the likely timeline of this revolution. And besides cars, we'll also take a look at flying motorcycles and take a brief trip to the year 2076 to imagine what the skies of these giant cities of the future will look like. Let's understand all of this. Hello, impressed viewers. I'm Realidad Impressionante, and you're watching Realidad Impressionante. Some cartoons from the last century imagined flying vehicles operating like small military fighter jets. But jet engines are expensive, noisy, and unfeasible for urban environments. And engineering has found a much smarter solution. That's when eVTOLs appeared, electric vehicles with vertical takeoff and landing. Functioning as a kind of large-scale evolution of modern drones, these aircraft use multiple electric rotors and operate at drastically lower noise levels. Companies like Jovem Aviation, Arx Aviation, and Volacotter turned what seemed like just a dream into a multi-billion-dollar industrial race. But the current race is following two completely different paths, okay? The first one is betting on so-called transition vehicles. Projects like the American Aleph Aeronautics and the Chinese Xpeng Aero HT are trying to combine road and sky in a single structure. When on the ground, they behave like conventional cars. But when necessary, retractable propellers or wings and also hidden propeller systems come into action to transform the car into a kind of aircraft. In other words, a real flying car. The second philosophy, by contrast, entirely abandons wheels. And instead of traditional cars, it relies on purely aerial capsules, designed to transport passengers between specific points in the cities, completely ignoring ground traffic. In this model, the automobile ceases to exist and gives way to a new suspended urban mobility network. And the revolution has also reached the world of motorcycles. The so-called hover bikes combine the riding position of a conventional motorcycle with extremely powerful rotors and turbines, capable of keeping the human rider suspended in the air. Projects like Jetson 1 have already proven that these technologies work, but physics still imposes severe limits. The battery range is still limited, and the huge airflow generated by the propellers makes it difficult to use them in densely populated urban areas. Because of this, the first uses should be on private property for agricultural monitoring, rescue missions, and special operations. And, my friends, if we look at the evolution of hardware and regulations, the future seems to follow a path that is quite clear. In the coming years, it's certain that urban skies will start to receive the first vertiports installed on top of corporate buildings, which will connect financial centers through fixed routes. A decade later, maybe more efficient batteries and autonomous systems will already allow trips of hundreds of kilometers without the need for human intervention. And if we move forward to 2076, then the very notion of traffic could change completely. Three-dimensional air corridors organized at different altitudes will be managed by artificial intelligence systems capable of coordinating millions of trajectories simultaneously. The big cities will stop being horizontal structures and will expand into a new layer suspended above our heads, just like science fiction made us imagine when we were little kids. Okay, but I'll make it very clear that in my opinion, flying cars won't happen the way science fiction really promised. Instead, quietly, modern engineering has found a much more realistic way to turn fiction into real hardware. Maybe, my friends, the future of flying cars isn't made of jet engines and floating avenues, but of a new layer of mobility built above our cities. And you, if you already had this option nowadays, would you still be dealing with the heavy traffic on avenues and streets? Or would you simply press a button and tell the AI to take you wherever you want to go? Let me know, okay? That really helps increase the reach of our channel's videos. Please leave a like if you can, it's really important. I'll show you the infrastructure for using these cars and motorcycles in our skies. This is already happening, you know? And there's no point in having a flying car in your garage or ordering one through an app if our cities are still stuck with the same infrastructure. Infrastructure from the last century, right? For the skies to become avenues, the world will need to build a completely new infrastructure, my friends. That's why engineers, architects, and aerospace companies are already working on this next idea, vertiports. These would be a kind of urban airport of the future. Unlike traditional heliports, which are designed to receive only a few aircraft at a time, vertiports were created to operate at high density. They will function as large smart hubs, capable of coordinating dozens of landings and takeoffs per hour. Acoustic isolation systems will reduce the noise from electric aircraft, while automated platforms will handle passenger screening and robotic arms will connect the ultra-fast chargers as soon as the vehicle touches the ground. Companies like Skyports, Ferrovial, and several projects supported by NASA and also by the FAA in the United States are already studying this type of infrastructure, which will serve as a bridge between the skies and the streets. The real challenge won't be building the suspended airports, but rather organizing thousands of aircraft that will be sharing the same airspace without turning the cities into three-dimensional chaos. The solution will be the creation of so-called digital airways. Instead of traffic lights or traffic officers, the airspace will be divided into altitude layers controlled by artificial intelligence. Short-distance vehicles will occupy the lower levels, while inner-city express routes will use the higher lanes. Cloud-connected software will continuously monitor the position and speed of each aircraft, automatically maintaining safe distances. Around schools, hospitals, and historic buildings, there will be invisible exclusion zones, true digital walls capable of preventing any unauthorized approach. And this new mobility will also transform the very architecture of cities. Skyscrapers will no longer be structures designed only for street level. The upper floors will have suspended lobbies, boarding areas, and even aerial garages for residents and visitors. The rooftops of buildings will become infrastructure as important as ground level. At the same time, the energy demand will be enormous. We can't forget about that. Smart power grids will need to supply hundreds of vehicles simultaneously, causing many buildings to consume more energy on their rooftops than old industrial factories used to. In neighborhoods, conventional parking lots and decommissioned gas stations could be transformed into micro-vertiports. These small hubs will serve for quick deliveries, shared air taxis, and emergency services. Over time, it will give way to a three-dimensional metropolis where the flow of people and goods will occur both on the streets and above them. In the early years, these infrastructures will be restricted to the wealthiest and to the financial centers of major capitals. But our history shows that all technology starts exactly this way. Man, it reaches the rich first, then eventually gets to us regular people. In the heart of Silicon Valley, the American startup Aleph Aeronautics has begun one of the most important phases in its history. The manual assembly of the first commercial units of the Aleph Model A, considered by many to be the first truly flying car. An electric car capable of legally driving on the streets and also taking off vertically. It represents an attempt to unite the road and the sky using just a single machine. Led by CEO Jim Docknow, the company is betting on a completely different idea from traditional eVTOLs, which resemble large drones or futuristic air taxis. The goal is to preserve the dimensions and appearance of a regular car, hiding all the flight technology inside the body itself. These guys already have thousands of reservations and a multi-billion-dollar order book. This way, Aleph tries to prove that urban aviation won't need to depend on airports, runways, or complex structures. The engineering behind the Model A may be the most intriguing part of this project. Its upper part is made of a carbon fiber mesh that is open and allows airflow to pass through to feed the 8 protected internal rotors. This eliminates those exposed propellers and reduces risks for pedestrians. During takeoff, the vehicle basically behaves like a large drone. However, when it starts moving horizontally, the entire external structure rotates 90 degrees, turning the sides of the car into a configuration similar to a biplane. Meanwhile, the two-seat cabin always remains level thanks to a gimbal system similar to the one used in gyroscopes. This allows the pilot and the passenger to remain seated normally while the rest of the structure changes position. And the specifications also reveal a very curious combination of safety and limitations. When on the ground, the vehicle has a range of approximately 322 kilometers and a speed limited to 40 km per hour in order to meet the low-speed urban categories. In the air, the range reaches about 177 kilometers, with a similar maximum speed. Obstacle sensors, independent motors, and even an integrated ballistic parachute have been added to increase safety in case of failures. Despite the advances, the obstacles remain enormous. Each unit is still handcrafted in San Mateo for intensive testing. The price of approximately $300,000 restricts access to a small elite, and FAA regulations require operators to have a private pilot's license. In addition, flights over densely populated urban areas are still prohibited at this initial stage. And while much of the world is still debating how to train pilots and adapt legislation for flying cars, Chinese engineering has decided to take a radically different path. Remove the human pilot entirely. Chinese company EHang is now among the world's leading firms in autonomous aerial mobility, with the EH216S, the first vertical takeoff and landing vehicle to achieve all the necessary certifications for mass production and commercial operations. The most impressive thing is that there is no one in command of the aircraft. There are no levers, pedals, or traditional instruments. Passengers simply get in, fasten their seatbelts, and select their destination on a touchscreen. From that moment on, all navigation is handled by artificial intelligence algorithms. During the journey, ground control centers operated by humans monitor everything in real time through high-speed communication networks, and they can remotely take control or order an emergency landing if any anomaly is detected. The entire vehicle architecture was built around the concept of redundancy. The structure uses 16 propellers powered by 16 electric motors that are independent from each other, distributed on 8 double arms around the carbon fiber cabin. The aircraft carries up to 2 passengers and supports a payload of approximately 220 kilo, reaches speeds of up to 130 kilometers per hour, and has enough range for urban trips of about 30 kilometers. If a motor fails, the others automatically adjust the power distribution to maintain flight stability. Getting to this stage required a real marathon of tests. For 3 years, the aircraft was subjected to simulated cyber attacks, deliberate GPS signal loss, and extreme weather scenarios. The engineers took the EH216, EH216S to operate under strong winds, intense heat, sub-zero temperatures, and even purposely induced mechanical failures. In some of the tests, 4 out of the 16 engines were shut down simultaneously in mid-flight. Even so, the algorithms redistributed the power of the remaining engines in fractions of a second, keeping the aircraft stable. And unlike many still futuristic prototypes, this platform already generates revenue today. The EH216S is marketed for around $410,000 to operators and governments. In cities like Shenzhen and Guangzhou, tourists pay between $40 and $60 for scenic flights of approximately 15 minutes. In addition, some specialized variants are already being used for cargo transport in mountainous regions, and even for fighting fires in skyscrapers. The progress of EHang shows that the future of air mobility may not depend on thousands of human pilots. And the real challenge, my friends, will be for us to learn to trust autonomous systems that will be able to make decisions on their own. All this while they're taking us from one place to another, above other people's heads. We'll need to trust the AI systems transporting us. Will you trust them? While much of the industry is rushing to create flying cars that are basically reinvented helicopters, a German company decided to take a slightly different path to show us something completely different. Instead of just connecting neighborhoods or making short flights over cities, Lilium aims to create an electric jet capable of linking entire urban centers quietly, and all of this without emitting a single molecule of carbon. The bottleneck of current aviation is quite evident. Traditional regional airplanes depend on long runways and consume fossil fuel on a large scale. On the other hand, many electric vertical takeoff and landing vehicles have limited range and were designed only for short distances. The Lilium jet aims to occupy exactly this intermediate space, combining the practicality of vertical takeoff with the aerodynamic efficiency of a conventional airplane. The secret of this aircraft lies in its architecture called DEPT, or simply electric ducted vectored thrust. Instead of using large external propellers, the design incorporates 30 small electric motors embedded in the moving surfaces of both the front and rear wings. During takeoff, these surfaces direct the airflow downward, causing the vehicle to rise vertically. When it reaches sufficient speed and altitude, the flaps smoothly rotate to the horizontal position, and the wings take over the lift, allowing the aircraft to fly like a traditional jet. The cabin was designed to carry the pilot and up to 6 passengers, and it can also be configured for quick cargo missions. This entire system has been optimized for energy efficiency. The expected range varies between 175 and 225 kilometers, which is ideal for connecting nearby cities and financial centers. The cruising speed can reach approximately 250 kilometers per hour, while the noise produced is drastically lower than that of conventional helicopters, making it possible to operate near urban areas without causing the same noise pollution. After completing the fundamental tests of transition between vertical and horizontal flight, the Lilium factory in Germany is now focusing its efforts on certification with the relevant authorities in Europe and the United States. The first planned markets include Florida, Bavaria, and the United Arab Emirates, with commercial operations projected for the end of this decade. Now imagine crossing the sky of a metropolis at over 300 kilometers per hour in a personal vehicle powered solely by jets. No giant propellers, no folding wings, and none of that giant drone look. Unlike traditional flying cars, the speeder was designed to take up as little space as possible. The company's proposal is to create a platform capable of naturally integrating into the cities of the future, using only compact areas for takeoff and landing. And its silhouette resembles a robust motorcycle more than a conventional aircraft, allowing the system to operate in places where larger vehicles simply couldn't function. Instead of relying on propellers or large exposed rotors, the speeder uses 8 synchronized microturbines electronically controlled by software. This vectoring system automatically distributes thrust among the engines, thus ensuring stability during all phases of flight. The absence of external propellers reduces risks and offers greater resistance to turbulence caused by wind corridors between skyscrapers. That's one of the main challenges of urban air mobility. The maximum speed can exceed 320 kilometers per hour, allowing urban and inner-city routes to be covered in a fraction of the time needed by conventional cars or helicopters. The carbon fiber structure supports approximately 270 kilos, meaning it can carry up to 2 occupants with luggage without compromising stability. In addition, the turbines have already been developed to operate with sustainable aviation fuels in the future, although they can currently use conventional fuels. But turning such a powerful machine into a product for civilian use requires extreme levels of safety. The speeder uses a fly-by-wire architecture controlled by artificial intelligence, which is responsible for making thousands of corrections per second. The human pilot doesn't need to control each engine individually, just simple commands, while the computer, or the AI in this case, prevents dangerous maneuvers and keeps the aircraft stable automatically. And since we started talking about motorcycles, for most enthusiasts of this type of vehicle, a machine with 4 wheels and electric power would already be enough to challenge the limits of conventional design. But the Frenchman Ludovic Lazare decided to go much further than that. Instead of choosing between the asphalt and the skies, he tried to unite these two worlds in a single creation. With a simple touch of a button, the futuristic motorcycle opens its wheels, reveals its high-speed turbines, and transforms into a machine capable of defying gravity. And it has already flown out there, my friends. Developed by the legendary French designer, the LMV 496 completely breaks this division between motorcycles and aircraft. The secret lies in its mechanical transformation system. In about 1 minute, the suspension arms move the 4 wheels into a horizontal position, creating space for the activation of a set of thrusters derived from the aerospace industry. It's a true transforming machine, coming straight from science fiction into real life. But lifting a vehicle weighing about 140 kilos off the ground without the help of wings? That requires an absurd amount of power. In the center of each wheel, there's a German JetCat turbine that can spin at an impressive 96,000 revolutions per minute. Working together, the 4 jet engines generate thrust equivalent to about 1,300 horsepower. To withstand the heat and external vibrations, the structure uses a combination of carbon fiber and Kevlar, materials normally found in the aerospace industry and in military applications. And controlling a machine powered by turbines also requires sophisticated electronic control. An onboard computer equipped with artificial intelligence, inertial sensors, and gyroscopes constantly monitors stability, making automatic micro-adjustments to the power of each turbine. On the streets, the LMV 496 operates like a conventional electric vehicle and has a range of about 160 kilometers. And despite all this powerful demonstration of engineering, physics still imposes severe limitations, The turbines consume kilos of jet fuel at an extremely high rate, limiting flight time to about 10 minutes per refueling. It sure guzzles fuel, huh? Besides that, only 5 units have been produced worldwide, each valued at around $560,000, making the LMV 496 one of the most exclusive and radical machines ever created. Despite the advances, there are still major obstacles, my friends. Regulations, urban air traffic management, and the transition to low-emission fuels remain the biggest challenges for the widespread adoption of our aviation technology, or flying cars, if you prefer to call them that. And yes, for the first time, that vision now seems much closer to physical reality than many people imagined back then. I believe that in the coming years and the years ahead, our world will be completely different from what we have today. What about you? How do you view our world's future, especially in transportation, since that's the video's topic? If you enjoyed this episode, please like and make sure you're subscribed. You have 2 new suggestions on your screen. Just click one, and I'll see you in the next video. Thanks for watching, and bye.